When we consider equilibrium, we also need to consider the types of changes which occur in equilibrium. So this includes both the chemical changes and the physical changes. And so mainly in equilibrium, at a molecular level, we would be focusing on the chemical changes, whilst the physical changes would be something we would be looking at an observable level. So the chemical changes are going to be when the matter changes its chemical identity. And so this results from the chemical reaction occurring itself. Whilst a physical change is when the matter changes its form or structure, but remains chemically the exact same. And so these are going to be two completely different subtypes of reactions, and so this will determine whether they're going to be reversible or irreversible. So we know that a chemical change is going to be irreversible because when we proceed with the reaction, there is a change in the chemical identity, and so this means that that can't be reversed back. However, with a physical reaction, the matter changes its form or structure but remains chemically the same, and so that means that that reaction can be reversed back the other way in order to go back to that original structure because the chemical identity of it hasn't been affected. And so some examples of these are, with our chemical reactions, we've got rusting, rotting, burning, and cooking. So those are all examples of real life chemical reactions. Whereas physical reactions, they're going to be the ones which you consider reversible. So things like boiling, melting, crushing a can, or breaking a glass. So although those may not be, the last two may not be considered something reversible necessarily, it hasn't fully changed the chemical structure of the product, and so hence it, on a chemical level, it can be considered reversible. So now we need to look at the concept of reversible and irreversible in order to define how we can apply this to equilibrium. So physical changes, as we said before, are usually going to be reversible. So for example, water can be cooled to stop it from being boiled, ice can be refrozen again, a crust can may be bent back into shape, and broken glass may be melted and recast back into its original shape. However, chemical reactions, they're going to be irreversible. And so examples of this is if we were to burn a piece of paper, that's going to be a chemical change that turns that paper into ash, and so that hence that ash can now no longer be turned back into paper because it's changed its chemical identity. And so now if we define equilibrium, the definition of equilibrium is that in a chemical reaction, chemical equilibrium will be the state in which both reactants and products are present in concentrations which have no further tendency to change with time, so there are no observable changes in the properties of the system. So essentially what we can say is that the rate of the forward reaction, it has matched the rate of the reverse reaction, and so because we have an equal rate at which the products are being produced from reactants, but then also an equal rate at which reactants are being produced from products, there's going to be no observable change on the observable level of the system. And then on the molecular level of the system, we've got both the forward reaction and the reverse reaction occurring at the same rate. So when we consider this, we consider the concept of reversibility. So we know that some chemical reactions are going to be reversible, and if they are reversible, they're depicted with the bidirectional arrows. And so it's really important to note that in any reversible reaction, the forward and reverse reaction are always happening simultaneously, just at different rates. So if we were not at equilibrium in the reaction and we were producing more of the product, we would be saying that the product direction of the reaction is being favored, and there would still be some reactant being reformed from the products. However, that would be occurring at a slower rate than the rate at which the products are being formed. So for example, we've got these two reactions here. We've got CaCO3 forming calcium oxide and carbon dioxide. And so if the rate of the forward reaction was to be faster than the rate of the reverse reaction, we would see that there would be more carbon dioxide being produced and more calcium oxide being produced, and that we'd be having a diminishing amount of CaCO3, the calcium carbonate. However, if we had the reverse reaction favored, we would have a reducing amount of calcium oxide and a reducing amount of carbon dioxide and an increasing amount of calcium carbonate. And then if we were at equilibrium in this particular reaction, we wouldn't notice any observable changes because on the molecular level, there would be the same rate of the forward reaction and the reverse reaction. Similar with this reaction below, where we've got water turning into water vapor. If we were to have this reaction occurring in particular conditions based on temperature, if we were favoring the forward reaction, we would notice a loss of water and a greater formation of the water vapor, whereas if we were to notice at a lower temperature, there would be less of the water vapor being produced, and the water vapor would be condensing to form liquid water. And so the point at which the forward and the reverse reaction are going to be occurring at the exact same rate, and hence there being no observable changes, is going to be what we call the dynamic equilibrium. So dynamic meaning that the forward and the reverse reactions are both happening simultaneously, but it's at a state of equilibrium, so there's no observable changes. And so if the forward reaction is going to be endothermic, so meaning that the forward reaction would be absorbing heat, then the reverse reaction would be exothermic because the reverse reaction would be giving off heat. And that's because with an endothermic reaction, we consider heat to be like a reactant because we're using heat in order to drive the reaction. So then in the reverse direction, heat would be like a product because it would be being produced by the reaction. So the reverse reaction would then be exothermic because it would be giving off heat.